All right. So I think I figured out the format that I'm going to choose for all future videos for now. For most, um, there's going to be times where I just don't feel like writing much or typing much, but I think it needs to incorporate my content should incorporate the things that I need in order to grow the fastest and the most steady. And so I can just sort of automate this task where I just upload several videos a day. I'm just having a hard time right now. I'm going through every time I resolve some things in my life, I have to realize how to incorporate all the things that I've learned into this new way of living. And so I it basically takes all of my brain power to overcome the mental hurdles that I've built for myself. Oh, I can't do that. Oh, why would I do that? Like things like that. A lot of the things that I do now, I used to be very against just because I didn't understand. So, but yesterday or the day before, I posted a video called Virtual Teaching. And I think that's the way I want to do it. So I'm going to take the digital textbook and I'm going to just basically write inside the digital textbook because I can. And then if there's any problems I need to work on, I can just go hop in to Google Keep and just write down some of this shit. So pretty sweet how it's set up. But yesterday was the first day that I felt like I needed to try dividing up the courses in a different way because the way I was doing it was based on ideas that I'm trying to get away from, trying to get away from like the normal conception of time and stuff. It's just a clock. So I've broken down all of the books that I'm reading, the Openstax books. Those are my priorities since the beginning. I've been thinking about these books for at least a year now. Um, so economics, philosophy, U.S. history, algebra, trig, anatomy, physiology, astronomy, biology, chemistry, physics, anthropology, psychology, and sociology. Obviously, those aren't all of them, but these are like the main ones I could do all at once without really conflicting with anything else. Um, and so economics has 34, philosophy is 12, and there's 32, 13, 28, 30, 47, 21, 17, 20, 16, 21, respectively, based on all the subjects that I read before. And each chapter has, in blue, a number of sections. So 4-3-5-3, 4-3-5-4-2-2, so on. 4-6-3-3-5-4-5-5-6, so on. 3-4-4-5-5-4-4-4-5-5-4-4-4-5-4-4-4-4, so on, and so on. And the goal is each time I complete a chapter, I can go to this Excel spreadsheet. It's all about coming full circle. Um, and I can change the color of one of these. The color is arbitrary, green and yellow. It's just what I chose. Um, so, as you can see, I've gotten one section of the 6 sections of Chapter 1 finished in Algebra Trig. So, the goal is really just to kind of tackle after all of these in a section before moving on to the next set. That way I'm getting a sort of more universal education here. And then I guess just in my free time when I'm not doing Instacart and when I'm not being lazy, just kind of working on this. And it makes sense that I really need to talk about this now because every month for the last several years, I have done nothing during the first 2 weeks of the month. And so I'm trying to get away from that. And this should help me do that. But the idea is I really want to finish all of these books, within a reasonable time frame, of course. Would be sweet if I could finish them before next year, but I just don't know how fast I can read. I haven't really committed myself. I need to commit myself to this, though, because this is the future of all the projects that I want to work on. So, all right. Let's put back Algebra Trig. No. Okay. Download PDF. Go to file. Two? No. One. Okay, that's 1.3. Point two. Okay. Read that. Do that. And then. Oh. That's why. Okay. Let's do it. All right. Algebra Trig, Openstax, section 1.2. Exponents and scientific notation. Learning objectives. In this section, you will use the product rule of exponents, use the quotient rule of exponents, use the power rule of exponents, use the zero rule of exponents, use the negative rule of exponents, find the power rule of a product and a quotient, simplify exponential expressions, use scientific notation. This is going to be 10.6. And 2028. All right. Mathematicians, scientists, and economists commonly encounter very large and very small numbers, but it may not be obvious how common such figures are in everyday life. For instance, a pixel is the smallest unit of light that can be perceived and recorded by a digital camera. A particular camera might record an image that is 2,048 pixels by 1,536 pixels, which is a very high-resolution picture. It can also perceive a color depth, which is gradations in colors, of up to 48 bits per frame, and can shoot the equivalent of 24 frames per second. The maximum possible number of bits of information used to film a 1 hour, 3,600 second digital film is then an extremely large number. Using a calculator, we enter 2048 times 1536 times 48 times 24 times 3600 and press enter. The calculator displays 1.304596316E13. What does this mean? The E13 portion of the result represents the exponent 13 of 10. So there are a maximum of approximately 1.3 times 10 to the 13 excuse me, bits of data in that one large film. In this section, we review rules of exponents first and then apply them to calculations involving very large or small numbers. So 1.30459316 E13 is the same as saying 61395 So it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Let's put some commas, comma, comma, and comma. So that's thousands, hundreds of thousands, hundreds of millions, hundreds of billions, 13 trillion. Is represented as this number. I could actually even approximate that by saying that's approximately 1.30 times 10 to the 13th power. Sorry. Just to show you what the different representations of it is. I prefer this format here because that's actually the calculator that I use. The TI-36X Pro by Texas Instruments. One of the most amazing calculators on the planet. It's so cheap. It's so simple. It's so versatile. It can solve derivatives. It can solve integrals. It can do all sorts of stuff. It could. I love the math print. So let's go here, back, there. Oops. Okay. So TI. So this is let's do 10, 6, 2033. So the TI-36X Pro has an interface that allows you to split a numerator and a denominator, and you can write complex stuff here. So this can be fractions. You can have trig functions. You can have exponentials. You can have logarithms. You can have all sorts of stuff. You could do something like log base 10 of x squared plus 5 over 3e to the 4 x squared. Like you could type that in all like that. All numerator as one function and denominator as one function, and then have it separated by this little divider line, which makes the whole thing itself a function. Such a cool, cheap calculator. It's like $20. It's my favorite calculator, though. They have some scientific calculators for the cell phone that you can use that are very similar to that. But yeah, I really like it. All right. Let's head back to the book. Using the product rule of exponents. Consider the product x cubed times x to the 4th. Both terms have the same base, x, but they are raised to different exponents. Expand each expression and then rewrite the resulting expression. So x to the 3rd times x to the 4th equals x times 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 x. So 7 x's. So we have 3 factors times 4 factors, but that's the same as just saying there's 7 factors of the same x. So we can condense it back down to x to the 7. So that means x to the 3rd times x to the 4 is the same as x2 and to the power of 3 plus 4, which is x to the 7. So, notice that the exponent of the product is the sum of the exponents of the terms. In other words, when multiplying exponential expressions with the same base, we rewrite the result with the common base and add the exponents. This is the product rule of exponents. A raised to the m power, where m is just any number, times a to the n power, where n is any number, or integer. We'll just say positive or negative integer. So you get equals a to the m plus n power. And that's just going to work with all of it. We can always check that this is true by simplifying each exponential expression. We find that 2 to the third is 8, 2 to the 4 is 16, and 2 to the 7 is 128. The product 8 times 16 equals 128, so the relationship is true. We can use the product rule of exponents to simplify expressions that are a product of two numbers or expressions with the same base but different exponents. So then right here, the product rule of exponents. For any real number a and natural numbers, so natural numbers being the counting integers, from 1 to infinity, m and n, the product rule of exponents states that a to the m times a to the n equals a to the m plus n, and that also includes the negatives 2 and 0. With that. Example 1. Write each of the following products with a single base. Do not simplify further. So this is going to be 5 plus 3. B. So that's going to be 5 plus 1 equals 6. Yep. And then that's going to be 2 plus 5 plus 3 equals 10. Yep. Cool. Using the quotient rule of exponents. The quotient rule of exponents allows us to simplify an expression that divides two numbers with the same base but different exponents. In a similar way to the product rule, we can simplify an expression such as y raised to the m divided by y raised to the n, where m is greater than n. So consider the example y to the 9 divided by y to the 5. Perform the division by canceling common factors. So y to the 9 times or divided by y to the 5. So if we just spread that out, you get y multiplied 9 times divided by 5 y's multiplied by each other 5 times. Sorry. And then so 5 of the y's on the top will cancel out with all 5 y's on the bottom, and you're left with 4 y's on the top, and that gives you just y to the 4th. So the rule, notice that the exponent of the quotient is the difference between the exponents of the divisor and the dividend. So a to the m divided by a to the n equals a to the m minus n power. In other words, when dividing exponential expressions with the same base, we write the result with the common base and subtract the exponents. So y to the 9 over y to the 5 equals y to the 9 minus 5 equals y to the 4. For the time being, we must be aware of the condition m greater than n. Otherwise, the difference m minus n could be 0 or negative. Those possibilities will be explored shortly. Also, instead of qualifying variables as non-zero each time, we will simplify matters and assume from here on that all variables represent non-zero real numbers. So the quotient rule of exponents, there's that little circle. For any real number a and natural numbers, that's the, those are the counting integers, my bad. Yeah, so they're just using the positives, my bad. The natural numbers m and n, such that m is greater than n, the quotient rule of exponents states that a to the m over a to the n equals a to the m minus m. So example 2. Write each of the following products with a single base. Do not simplify further. So first one is 14 minus 9. That's 5. That's 23 minus 15. A second, ordinary arithmetic. 5 plus, what is that, 8? 9? 8? 8. And then 5 minus 1 equals 4. 5 minus 1 equals 4. 23 minus 15 equals 8. 14 minus 9 equals 5. Using the power rule of exponents, suppose an exponential expression is raised to some power. Can we simplify the result? Yes. To do this, we use the power rule of exponents. Consider the expression x squared third or cubed. The expression inside the parentheses is multiplied twice because it has an exponent of 2. Then the result is multiplied 3 times because the entire expression has an exponent of 3. So x squared cubed equals x squared times x squared times x squared, which equals x times x times x times x times x times x, which equals x times x times x times x times x times x. That's just x 6 times, so that's x to the 6th. The exponent of the answer is the product of the exponents. X squared cubed equals x times or x to the 2 times 3, which equals x to the 6th. In other words, when raising an exponential expression to a power, we write the result with a common base and product of the exponents. So a to the m raised to the n equals a to the m times n power. Be careful to distinguish between uses of the product rule and the power rule. When using the product rule, different terms with the same bases are raised to exponents. In this case, you add the exponents. When using the power rule, a term in exponential notation is raised to a power. In this case, you multiply the exponents. So, and then here's just the example. I don't need to go through that because it's pretty straightforward. So the power rule of exponents defined: for any real number a and positive integers m and n, the power rule of exponents states that a to the m to the n equals a to the m times n power. So, example 3, use the power rule. Write each of the following products with a single base. Do not simplify further. So, this is like saying, so that's 2 to the 7, so that's 2 times 7 equals 14. And this is like saying 5 to the third, so that's like 5 times 3, 15. And that's the same as like 5 times 11, 55. 2 times 7, 14. 5 times 3, 15. 5 times 11, 55. Using the zero exponent rule of exponents, return to the quotient rule. We made the condition that m greater than n so that the difference m minus n would never be 0 or negative. What would happen if m equals n? In this case, we would use the zero exponent rule of exponents to simplify the expression to 1. To see how this is done, let us begin with an example. So t to the 8 divided by t to the 8 is the same as saying 1. If we were to simplify the original expression using the quotient rule, we would have t to the 8 over t to the 8 equals t to the 8 minus 8 equals t to the 0. If we equate the two answers, the result is t to the 0 equals 1. This is true for any non-zero real number or any variable representing a real number. The sole exception of the expression 0 to the 0. This appears later in more advanced courses, but for now, we will consider the value to be undefined. Okay, go ahead and do that. So the definition for the zero exponent rule of exponents: for any non-zero real number a, the zero exponent rule of exponents states that a to the 0 equals 1. Example 4. Using the zero exponent rule. Simplify each expression using zero exponent rule of exponents. So we have 3 minus 3. That's a 0. We can split this up. That negative 3 can come out and be its own guy, and we can multiply that. So x to the 5th divided by x to the 5th, that's 1. So this is negative 3. C. Well, there's j squared k is the variable. So all of them have the same base. There's 4 of them on the top and 4 of them on the bottom, so that's 0. And then rs squared is the base, and they're both squared, so that's just 5. So we have negative 3, 1, negative 3, 1, 5. 1, -3, 1, 5. Using the negative rule of exponents, another useful result occurs if we relax the condition that m is greater than n in the quotient rule even further. For example, can we simplify h cubed over h to the fifth? When m is less than n, that is, there is a difference, m minus n is negative, we can use the negative rule of exponents to simplify the expression to its reciprocal. Divide one exponential expression by another with its larger exponent. We use the example h cubed over h to the fifth. So h cubed over h to the fifth, go ahead and distribute that out. So you got 3 h's over 5 h's. So there's the common amount in both is 3, so we cancel 3 out. So you get 1 over h squared, or 1 over 2 h's, which is the same as 1 over h squared. So that's the same as saying h to the negative 2. So putting the answers together, we have h to the negative 2, which equals 1 over h squared. This is true for any non-zero real number or any variable representing a non-zero real number. A factor with a negative exponent becomes the same factor with a positive exponent if it is moved across the fraction bar from numerator to denominator or vice versa. So a to the negative n equals 1 over a to the n, and a to the n equals 1 over a to the negative n. We have shown that the exponential expression a to the n is defined when n is a natural number, 0, or the negative of a natural number. That means that a to the n is defined for any integer of n. Also, the product and quotient rules and all the rules we will look at soon hold for any integer of n. So let's go ahead and circle definition. The negative rule of exponents is defined as, for any non-zero real number a and natural number n, the negative rule of exponents states that a to the negative n equals 1 over a to the n. Example 5. Using the negative exponent rule, write each of the following quotients with a single base. Do not simplify further. Write answers with positive exponents. So we have theta to the third over theta to the 10. So that's going to be theta to the 1/7, or theta to the negative 7. Theta to the negative 7th power. So we have z squared times z over z to the 4th. So they all have z as a common base. So there's 3 in the top, 4 at the bottom. So that's going to be z to the negative 1. Z to the negative 1 power. So 5t cubed, so that's our base. So negative 5t cubed to the 4th and to the 8th, that's just negative 5t cubed to the negative 4th. Yep, to the negative 4th, to the negative 7th, to the negative 1. Cool. Example 6. Using the product and quotient rules, write each of the following products with a single base. Do not simplify further. Write answers with positive exponents. So b squared times b to the negative 8. So b squared times b to the negative 8. That's the same as saying b to the 2 minus 8 equals b to the negative 6. So negative x to the 5th times negative x to the negative 5th, that's just going to cancel each other out. That's going to be 1. And then negative 7z over negative 7z to the 5th. So negative 7z is the base. So that's 1 minus 5, negative 4. Negative 7z to the negative 4. Yep. Right? Finding the power of a product. To simplify the power of a product of two exponential expressions, we can use the power of a product rule of exponents, which breaks up the power of a product of factors into the product of the powers of the factors. For instance, consider pq cubed. We begin by using the associative and commutative properties of multiplication to regroup the factors. So pq cubed equals pq times pq times pq, which is the same as P times Q times P times Q times P times Q. And we can rearrange. So we have 3 factors of P and 3 factors of Q all multiplied by each other. So then you get P cubed times Q cubed. So PQ cubed equals P cubed times Q cubed. So the definition of the power of a product rule of exponents is for any real numbers a and b and any integer n, the power of a product rule of exponents states that ab raised to the nth power equals a to the nth power b to the nth power. So example 7. Using the power of a product rule. Simplify each of the following products as much as possible using the power of a product rule. Write answers with positive exponents. So this is just going to be a cubed b to the 6th. 2 to the 15th, t to the 15th. Negative 8, w to the 9th. So that would be 1 over, so that negative will go away. 7 to the 4th, z to the 4th. This is just a big number. It's 49 squared. Okay, and then e to the negative 14, f to the 14. So, a cubed b to the 6th, large number, t to the 15th, negative 8, w to the 9th, yep, big number, z to the 4th, and then, yep, e to the negative 14, f to the 14. Okay, cool. Finding the power of a quotient. To simplify the power of a quotient of two expressions, we can use the power of a quotient rule, which states that the power of a quotient of factors is the quotient of the powers of the factors. For example, let's look at the following example. So e to the negative 2, f squared, all raised to the 7th, equals f to the 14th, e to the 14th. Let's rewrite the original problem differently and look at the result. So e to the negative 2, f squared to the 7th equals f squared over e squared, all raised to the 7th, and then you just distribute. It appears from the last two steps that we can use the power of a product rule of a quotient rule. So basically what they do is they turn it into a fraction, so f squared over e squared to the 7th, and then you separate the numerator and the denominator into separate functions with the exponent distributed to each, and then you do the power of the product rule, and then you're done. So, definition. The power of a quotient rule of exponents is defined as, for any real numbers a and b and any integer n, the power of a quotient rule of exponents states that a over b to the n equals a to the n over b to the n. So example 8, using the power of a quotient rule, simplify each of the following quotients as much as possible using the power of a quotient rule. Write answers with positive exponents. So 4 cubed is 64. Z to the 33rd. P to the 6th. Q to the 18th. Negative 1 over T to the 54. J12. K to the negative 8. M negative 6. N negative 6. Yep, 64. Z 33rd. P6. Q18. Negative 1 over T to 54. J12. K8. M6. N6. Yep, cool. Simplifying exponential expressions. Recall that to simplify an expression means to rewrite it by combining terms or exponents. In other words, to rewrite the expression more simply with fewer terms. The rules for exponents may be combined to simplify expressions. Oops. Let's see if there's a snip tool. Okay, no snipping tool. Is there a print screen button on here? Of course not. All right, so this first one is going to be 6 cubed m to the 6th n to the negative 3. So this is going to be 17 minus, so 5 minus 4 minus 3, negative 2. So this is going to be the same as v to the 4th over u squared. So I'm going to show you an easier way to solve something like this. So this is like saying, I'm just going to say that is x and that is y. So negative 3x times 5y. That's going to be negative 15xy. So then now I can redistribute that back in there. So negative 15 a cubed, b to the negative 1, a to the negative 2, b squared. And then these two could just multiply by each other. So it's just, since that's just one term and that's one term, it's all going to become one term. So negative 15 a b. One. This is the same as saying 3 with a 2 on the outside. So that's going to be 3w squared cubed over 2. So you have 216 m6 and negative 3. Yep. Oh, I screwed that up somehow. Oh, 17 to the negative 2. Yeah. Okay. That's right. Yep. Shoot, that's a 2, not a 3. 2, so that makes that a 10, and that's a 10. 1, 27w14 over 4. Yep. That's a cube, so that's 27. So oh, hold on. I screwed that up. Hold on. Oh, frick. There's a negative sign there. Yeah, I screwed that up. Okay. I don't care. All right. Using scientific notation, recall at the beginning of the section that we found the number 1.3 times 10 to the 13 when describing bits of information in digital images. Other extreme numbers include the width of a human hair, which is about 0.00005 meters, and the radius of an electron, which is about 0.1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 zeros, 4, 7 meters. How can we effectively read, compare, and calculate with numbers such as these? A shorthand method of writing very small and very large numbers is called scientific notation. in which we express numbers in terms of exponents of 10. To write a number in scientific notation, move the decimal point to the right of the first digit in the number. Write the digits as a decimal between 1 and 10. Count the number of places n that you moved from move the decimal point. Multiply the decimal number by 10 raised to a power of n. If you move the decimal left as in a very large number, n is positive. If you move the decimal right as in a small large number, n is negative. For example, consider the number 2.780418 million. Move the decimal left until it is to the right of the first non-zero digit, which is 2. So it moves 6 places. So you get 2.780418. We obtain 2.080418 by moving the decimal point 6 places to the left. Therefore, the exponent of 10 is 6. And it is a positive because we moved the decimal point to the left. This is what we should expect for a large number. 2.780418 times 10 to the 6, or 2.780418 E6, using the TI-36X Pro format. Working with small numbers is similar. Take, for example, the radius of an electron, lots of zeros, meter. Perform the same series of steps as above, except move the decimal place to the right. So it moves over 13 places. Be careful not to include the leading zero in your count. We move the decimal point 13 places to the right, so the exponent of 10 is 13. The exponent is negative because we move the decimal point to the right. This is what we should expect for a small number. 4.7 times 10 to the negative 13, or 4.7 E negative 13. So scientific notation is defined as: a number is written in scientific notation if it is written in the form a times 10 to the n, where 1 is less than the absolute value of a, 1 is less than or equal to the absolute value of a that is less than 10, and n is an integer. So what that is basically saying is that a or yeah, that's right. So basically it's going to be some one, oh sorry, hold on, eraser, that is just a greater than sign. Okay. So that means boom, 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 and then this is going to be plus or minus. This is going to be 1 through 9, or 1 through 9, 1 through 9, so on. That's not 1 divided by 9, that's 1 through. I was just trying to fit it. Okay, so example 10, converting standard notation to scientific notation. Write each number in scientific notation. So the distance to the Andromeda Galaxy from Earth is a lot. So that's decimal goes there. 1, 4, 7, 10, 13, 16, 19, 22. 2.4 times 10 to the 22. Diameter of Andromeda Galaxy, big number. So again, so that's there. So that's 3, 6, 9, 12, 15, 18, 21. 1.3 times 10 to the 21. Number of stars in the Andromeda Galaxy, 1 point times 10, 3, 6, 9, 12. Diameter of an electron, 9.4 times 10 to the 1, 2, 3, 4, or 12, 13, 14 meters. Probability of being struck by lightning in a single year, 1.43 times 10 to the negative 6. 22, 21, 12, negative 13. I did 14, so that means the 0 mixed up. Negative 6. Okay. Converting from scientific notation to standard notation. To convert a number in scientific notation to standard notation, simply reverse the process. Move the decimal n places to the right if n is positive, or n places to the left if n is negative, and add zeros as needed. Remember, if n is positive, the value of the number is greater than 1, and if n is negative, the value of the number is less than 1. So example 11. Converting scientific notation to standard notation. Convert each number to scientific notation to standard notation. So that's going to be 11 zeros, 5 zeros, 6 zeros. It's going to precede with 6 zeros. It's going to precede with 11 zeros. Using scientific notation and applications. Scientific notation used with the rules of exponents makes calculating with large or small numbers much easier than doing so using standard notation. For example, suppose we were asked to calculate the number of atoms in 1 liter of water. Each water molecule contains 3 atoms. The average drop of water contains around 1.32 times 10 to the 21 molecules of water, and 1 liter of water holds about 1.22 times 10 to the 4 average drops. Therefore, there are approximately 3 times, and then all those numbers, so you get approximately 4.83 times 10 to the 25 atoms in 1 liter of water. We simplify, or simply multiply the decimal terms and add the exponents. Imagine having to perform the calculation without using scientific notation. When performing calculations with scientific notation, be sure to write the answer in proper scientific notation. For example, consider the product 7 times 10 to the 4 times 5 times 10 to the 6 equals 35 times 10 to the 10. The answer is not in proper scientific notation because 35 is greater than 10. Consider 35 as 3.5 times 10. That adds a 10 to the exponent of the answer, so you get to the 11. Okay. Example 12. Perform the operations and write the answer in scientific notation. Okay, I'm just going to use a calculator for this one. Old trusty TI-36. 8.14 EE negative 7 times 6.5 EE 10. So that's going to be 5.291. So since we're not using proper rounding, I'll just keep all non-zeros. So it equals that. Okay. For EE negative 5. Oh, just regular 5, sorry. So, divided by negative 1.52, 9, 2.63158, E negative 4. So, I get that answer. So, yep. See if I can demonstrate one of these using 2.7, 6.04. So that's 8, 2, 10, 0, 0. It's 2, 4, 12, 16, 1, 6, 3, 0, 8, 3 decimals. So 4, so 1.6, 6308 times 10 to the 1. 513, 1819. Yep, times 7 to the 19. So that's how you do it. Okay. Example 13. In April 2014, the population of the United States was about 308 million people. The national debt was about 17 trillion, 547 billion dollars. Write each number in scientific notation, rounding figures to two decimal places, and find the amount of debt per U.S. citizen. So, debt per citizen equals 1,7,547,000,000,000,000 over 308,000,000. What I like to do, instead of just turning it into scientific notation, I can just cross out zeros. So we just go red, 3, 3, 3, 3. So we got that over 308. So that's the same as saying 1.7547 times 10 to the 3, 6, 7 over 3.08 times 10 squared. So our answer is going to be somewhere between 10 to the 4 and 10 to the 6. Yep, there we go. 5.4, 5.7 times 10 to the 4. Cool. And that's it for that section. So let's call that 2112. Smiley face. And let's just call it. So